Just one second. I saw this one. Finding the order of reaction in this question. This first thing, explain what is meant by the term by the following terms. What is the half-life? It's the time needed for the reaction to become half. Time required for the concentration of a reactant to decrease by half. To decrease by half. And the rate determining step is the slow step in the mechanism of the reaction. In the mechanism of a reaction. Now, this part over here, which we're going to do, is seeing the reaction between hydroxide ions and bromo ethane is first order with respect to OH ions and first order with respect to CH3Br. And it's just a practical method that would confirm that the reaction is first order with respect to OH ions. Your method should include, so I'll do this because this is more related to, this one is more related to paper 5, where you have to design experiments. So we're going to do this on the board over here. Just one second, I've lost the board. So now the question requires the details for designing an experiment which would allow you to figure out the rate of the reaction, the order of the reaction with respect to OH ions. And it's a 4-mark question, and they've given you plenty of space to answer this question. Now, when you're designing an experiment, now this is going to be specifically from an experimental point of view. You've got 2 reactants, and you have to figure out this relationship, that what happens when you alter the concentration of OH ions. So you're basically trying to figure out the rate, how rate would change when the concentration of OH ions varies. And you're trying to figure out the order A over here. This is what you want to figure out. So your method should include, it should be a practical method, and you have to figure out whether it's first order with respect to OH ion, and your method should include details of measurements that would be taken in order to calculate the rate of the reaction. So all you have to do is do several experiments. So you're going to do several experiments, and in those experiments, what you're going to do is you're going to figure out, you're going to vary OH ion concentration, and every time you vary the OH ion concentration, you're going to measure the rate of the reaction, and you're going to see how that rate changes with time. So that's all you have to do, but it's a 4-mark question. You have to be very specific with the details. How are you going to do? All other variables, they need to be constant. So the only thing you're trying to change, this is your independent variable, that's OH ion, and you change OH ion, the rate of the reaction would change. So that's your dependent variable. So you've got 2 variables. One of them is, hopefully you're familiar with independent. Independent variable is the one that you're controlling in the experiment. So that's the independent variable. And the rate of the reaction changes accordingly as soon as you change the concentration of OH, and that's your dependent variable. Now, when you're investigating this, all other variables, they got to be constant. So you have to keep all other variables, they need to be constant. So should be kept constant. And especially those variables that are going to affect the rate of the reaction. So especially those variables. So this relationship should not be affected by any of the other variables. They include temperature. So temperature has to be kept constant. So that's one. They also include, you can't have pressure because all of these things are affected by the rate of the reaction is affected by temperature. It's affected by pressure, but pressure will only affect gases. These are not gases. They're solutions. So pressure is not going to be, I mean, you don't need to keep pressure constant because pressure only affects gases. Surface area is, because both of them are solutions, there's no solid involved, so surface area is out of the question as well. There's no catalyst being used, so I mean you got to keep that constant, but there is no catalyst, so there's no point writing that. There's one other thing that has to be kept constant, and that's this other reactant, because there are two reactants. You're trying to figure out, if you change OH ion, how would the rate of the reaction change? So this other reactant, its concentration must be kept constant throughout the reaction. So one way to keep that constant is by adding it in large excess. So it's CH3Br. I think it was CH3Br. Yes. That should be kept in a very large excess. Because if you put anything that's in large excess, so CH3Br concentration has to be kept constant throughout the reaction so that it doesn't affect the rate of the reaction. So it is kept in large excess. So it is added in large excess. You add so many moles of it that even if a few moles get used up in the reaction, its overall moles would kind of remain almost the same. So it is added in very large excess. Okay, so you have to keep some of the variables constant. So these are the variables that got to be constant. Okay. Is this clear so far? Sam, Nadine, Hafsa, Zoha, is this clear?
Yes, sir.
So now, remember, you've got two variables. You've got an independent variable, you've got a dependent variable. In all experiments, it's pretty much the same thing. There's an independent variable and there's a dependent variable. And you're going to change this. So the next thing that you're going to do is you're going to vary OH ion concentration. So how are you going to do that? So varying OH ion concentration. So remember, in your reaction, you've got you're going to take CH3Br. So I'm just going to make a random table of the reactants that I got to add. So I'm going to take CH3Br concentration. Now to figure out this, the multiple methods. So I'm going to do method number 1 first. Now the first thing is CH3Br concentration, and is 0.1 mole per dm cube. And let's say you're adding, the volume that you're adding is 40 cm cube. So there's a table that you're going to make. The other reactant is your OH concentration. So you've got your OH concentration, and that one is in large excess. This one is 0.01 mole per dm cube. So this, I mean, the concentration used is 10 times greater, so that there's a lot more of CH3Br. I'm going to add OH ion, so the volume that I'm going to use in this reaction, that's going to be written over here. And remember, this has to vary. I mean, you have to vary this. So this kind of needs to change in every experiment. And then you're going to try and measure the rate of the reaction. So that's another thing that you have to worry about. How do you measure the rate of the reaction? So that's what you're going to try and do. So let's do experiment number 1. In experiment number 1, you're taking, for example, 50 cm cube of this, and you're mixing it with 50 cm cube of this other reactant, right? So that is experiment number 1. There needs to be another column over here, so I'll add that column. That's the amount of water added. So we're just going to make another column over here, which is, so that this, although all this detail is not required specifically for this question, but it would be very helpful in your P5s because you would have to design these. You might have to use these or make tables in it as well. So over here you have the volume of water added in cm cube, and initially it is 0 cm cube. So this is the first experiment, and you're going to somehow measure the rate of the reaction. We'll talk about that later. So remember, we are trying to vary OH concentration, and we're going to try and see how the rate of the reaction changes. The concentration of this CH3Br needs to be kept constant. So if you do the second experiment, it's going to be the same thing. That is again taken as 50 cm cube. And this time the OH volume used is now 40 cm cube. And you're going to mix 10 cm cube of water to it. So in that way, it gets diluted because now the concentration has decreased. The concentration of OH has decreased. It's now lesser because it's got diluted by water that's being added. The total volume has to be kept constant at all costs because you don't want the total volume of the solution to change, because if the total volume of the solution changes, the concentration of CH3Br would get affected, because remember, concentration is moles over volume. So you're adding always the same moles, so the volume of the solution should not change because these things are going to mix up, and the volume is going to be 100 cm. That's the total volume. So remember, if you're decreasing the amount of OH ions that you're adding into the solution, you have to add the same amount of water to make up the volume, because the total volume should not change, because you have to keep the concentration of CH3Br constant. I mean, if the solution volume changes, concentration is moles over volume. So you're adding the same moles, but the total volume would be lesser, which would alter its concentration. So that has to be kept constant. So at all cost, the reason you're adding the volume of water is you got to keep in every experiment all other variables that got to be constant. So keep the total volume of the solution constant. So basically what's going on is that every time when you mix them up, you always have 100 cm cube of total solution. The moles of CH3Br, let's say every time you're adding 50 cm cube, every time you're adding, let's say you're adding 5 moles. So its concentration always remains constant. Those 5 moles that you're adding, I'm just hypothetically speaking, those 5 moles that you're adding every time, they're always present in 100 cm cube of the total solution. So their concentration kind of remains constant, because if the total volume changes, then its concentration would change as well. So you have to keep, at all costs, you have to keep the total volume constant. Is this point clear?
Yes, sir.
Okay, so remember the OH concentration, by adding water, you're constantly changing that. And you're going to do several experiments. Every time you're going to do a third experiment. This time, again, you're going to add the same amount of CH3Br, and you're going to dilute this. So it's going to be 30 cm cube now. And to make the total volume constant, I'm going to add water. So the OH gets diluted even further. And so on. So the fourth experiment, there would be minimum, there should be 5 experiments, because you got to keep 5 experiments gives you, I mean, there is, if you do more experiments, the results are more reliable. So 50 cm cube, you decrease the quantity of OH, you just add 20 cm cube, and you dilute it further by adding 30 cm cube of water. And then the fifth experiment, that's going to be our last. So it's going to be 50 cm cube. This would be just 10 cm cube that's going to be used. And there's going to be 40 cm cube of water that's going to be added. Now, the concentration of OH is directly proportional to the volume that you're using. Because as the volume is going down, remember, concentration is moles over volume. So you're adding fewer and fewer moles, and you're adding more water to it. So it gets diluted. So that this one is the most dilute, because you just added 10 cm cube of it, and you added 40 cm cube water into it. So this last one is the most dilute. The first one is the most concentrated. So concentration of OH is varying as the volume. So concentration of OH is directly proportional to the volume that you're using. Is proportional to, so it's proportional to the volume that you're constantly adding. So anyway, so that's how you're going to do several experiments. So remember, coming back to this, you have to figure out, you've learned how to alter the concentration of OH. Now, how would you measure the rate of the reaction? That is something that's got to be measured. The rate of the reaction. Now, the rate of the reaction, specifically in this particular example, remember, rate we did previously. Rate is any change. If I do it over here and explain it again, so experimentally, rate is any change that's happening with respect to time. So it's any change that's going on with respect to time, and you're going to measure how quickly that change happens. And usually we're interested in the initial rate, because all rates they vary with time. The reactions, they're fast in the beginning and then they slow down. So the value of the rate is constantly changing for a reaction. So we're interested in the initial rate right at the beginning. That is what we are interested in, the initial rate. So what you're going to do is what you're going to do what you're going to do in this case is, what specific change could you measure with respect to time? Now this one has OH ion concentration, so it's going to be alkaline initially. So what would happen is that the pH would change, and so what you can do is, so the pH would constantly change. So you can measure the OH ion concentration with respect to time by measuring the pH of the reaction. Or what you could do is, so you're saying your method should include measurements that will be taken in order to calculate the rate of the reaction. You could also do titration, like right after the after a few seconds, you can stop the reaction and titrate it with HCl and figure out how many OH ions are left in the reaction mixture. So you could do all of those. So rate of the reaction would be proportional to 1 over time. You're going to keep a fixed mark. It has changed with respect to time. So you're going to keep the change fixed. Like if there's a 100-meter race, no one actually goes and measures the actual meters per second, or they don't measure the speed. They don't measure the change with respect to time. They just measure time. That's it. Because if there's a 100-meter race, whoever reaches there first, whoever has lesser time, or whoever, I mean, what you're going to do is, if there's a 100-meter race, there's everyone has different times. So rate is inversely proportional to time, which basically means that if it takes lesser time, the reaction is faster. So you're going to make the change fixed. I mean, the mark should be fixed. Like if there's a 100-meter race, everyone has to reach that mark, and you're going to measure their time. That's it. So there's no point calculating this. You can just measure the time. That's it. So what we are going to do is we're going to probably just measure when does the solution become neutral? How much time does it take? So you can have a pH meter and you can just time it. What time is required for the solution for all the OH ions to get used up. So if the reaction is really, really fast, the OH ions would react very quickly and the solution would become neutral very, very quickly. If the reaction is very slow, it's going to take a much longer time, and the OH ions will get neutralized after a longer time. So we can have a fixed change. Remember, like a 100-meter race, we need a mark. Like all our 5 experiments, they need to reach that mark, and we're going to time them. So in this case, we can state that our changes against which we are measuring the time. Okay, so imagine there are 5 experiments, there's a race going on. So in our case, our changes, how long does it take for the solution to become neutral? Okay, is this clear?
Yes, sir.
And you're going to time this. So you'll get you'll time this, you'll have a pH meter, and you'll start the reaction, you're going to add these things, and then you'll have a stopwatch in your hands, and you'll just keep measuring the pH after, let's say, every 2 seconds. And then when it goes neutral, that's when you stop the stopwatch. That's it. So the first one is probably going to be the faster one. It's going to take a lesser time. The last one is going to be the slower one, and it's going to take a longer time. So you'll get 5 different rate values. I mean, you're going to get 1 over T. Now, the next thing is, what do you do with this? How do you figure out the order of the reaction, which is this one? Like, how do you figure out A from this? So one way to do this is, remember, in physics and in chemistry, whenever you have any relationship between variables, what you try to do is you try to convert that relationship into a linear relationship, like a straight line. And you go and try and measure the gradient of that. So we have this relationship, which is rate is proportional to OHN concentration, and we don't know what the order is. So we have this relationship. I need to convert that into, now this is clearly not a straight line. So what we can do is we can take log on both sides. Now, if I take log of rate, and we can introduce okay, let's keep the proportionality sign for now. So we can take log on both sides. Now, if I take log on both sides, what log does is that the power becomes, whenever you take a log of something, like, I mean, this is the property of log, that if you take the log of 2 to the power 4, and if you take the log of this thing, then this actually becomes 4 times log of 2. So that's a property of log that you need to know. I mean, it makes sense. What log does is it expresses a value of something in the powers of 10. So that is what a log does. Like, if you take the log of 10 power 2, then this is actually equal to 2 times log of 10. Log of 10 is 1. I mean, what is 10? 10 to the power 1 is 10. So log of 10 is 1. So this gives you 2, which makes sense, because 10 power 2, express that in 10 in the power of 10, that would be 2. So this is a property of log, that any power, it becomes a coefficient. So when you take the log, in this case, you'll get log of rate proportional to A times Acha, so when you take this, you get this. Now this one is a relationship which is equal to y is equal to mx, or y proportional to mx. Like, if I get rid of the proportionality sign, there's going to be a c. So that's basically equal to y is equal to mx, and m over here is going to be your order. So x is going to be the constant log of the concentration of OH ions. You're going to plot that, and y is going to be the log of rate. And when you plot these two things, the gradient is going to be the order. So gradient is order. So remember, we're trying to figure out this power A. We had the rate values from our table, and rate was proportional to 1 over time. We had the concentration values, that concentration, it varied as the volume of OH ion added kept becoming lesser and lesser, and the volume of water added, you were diluting it. So you had all of that. You were changing OHN concentration, you were changing the rate. The rate was a dependent variable, so it was changing accordingly. When you took log A became the coefficient, and your equation became in the form of y is equal to mx. And if you're going to plot y and x, which is x over here is log of OHN concentration, on the y-axis you're going to plot the rate. The gradient would be your order of the reaction. So this is what you're going to do. So on one axis, so you'll have two axes, and on one axis you'll plot the log of OHN concentration, and on the other axis you're going to plot the log of rate. And you're going to get a straight line, some random straight line, and the gradient of that, I mean, the points would not be all on the same line, it would be a best fit line, and the gradient is going to be it's going to give you the order. So if it's zero, if the order is zero, that means you keep on changing OHN concentration, the rate does not change. So that means the gradient is zero. It's going to be a straight line. The rate does not change. So that means OHN concentration, the rate is not dependent on that. If it's order one, that would be a line with gradient one. If it's order two, that would be a much steeper line. So this is what you're going to do. And a rate in your case is 1 over t. So basically it's I mean, you took rate as being proportional to 1 over t. So in your case, it's actually log of 1 over time. And the OHN concentration was proportional to the volume. So in your case, it's basically the log of the volume of OHN concentration, OHNs that you're using. Because if you go back, it's rate was 1 over t, and the concentration of OHN varied as the volume added decreased. So it was proportional to that. So you can plot the volume of OHNs and its log versus the rate that you're calculating, which is 1 over t. And you're going to try and find what the gradient is going to be. Is this clear, this example?
Yes, sir.
Okay, so I'll just go back and just go through this once more. So remember, he wanted us to measure the OHN concentration. So he wanted us to investigate how the rate varies as you change the OHN concentration. So you have to figure out the order. 0 means it doesn't vary. 1 means it's directly proportional. 2 means it's a quadratic relationship. So you're going to keep CH3BR, you're going to keep all other variables constant. And that would include the total volume that you're going to add into the solution. So every time you do an experiment, every other variable has to be constant, except for your independent and your dependent variables. Your dependent variable is obviously not going to be constant because it's going to change as you change the independent variable. So this is how you're going to change or vary OHN concentration. By adding an equal amount of water, you're going to dilute it. And you're going to measure rate by measuring a change, a specific change. It could be any change with respect to time. And you keep measuring that change over time. And once you do that, you can rate is 1 over time, is inversely proportional to time. Lesser time, that means faster reaction. And you're going to convert the relationship into a linear relationship, which is y is equal in the form of y is equal to mx. You're going to take log on both sides, and you're going to plot log of OHN concentration, log of rate, and that would give you a line, and the gradient of the line is the order of the reaction. Now, the other thing that you could have done, which would have been much easier, would probably be that you plot a half-life graph. Just a second. So the other thing that you could have done was this one. You could have done just one experiment, but you would have measured the OH ion concentration at regular intervals by measuring the pH. Remember, the pH can be turned into the OH ion concentration. The pH and OH ions are, if you remember equilibria, from pH you can measure pOH, and from pOH you can measure the OH ion concentration. So by measuring the pH, you can just do one experiment, and you can track the OH ion concentration as it varies with respect to time. So depending on the shape of the graph and depending on the half-life, you can also figure out the order with respect to OH ion by this method as well, which would have been much easier, but kind of less reliable because it involves only one experiment. Just take one experiment, OH ion concentration, and measure the rate or measure the concentration of OH ion after very regular intervals until the reaction ends. And the shape of the graph would tell you what order it is, but it's just less reliable because you're just doing one experiment. Okay. So is this clear? This thing?
Yes, sir.
So let's then continue tomorrow. We'll try and start a new topic tomorrow. Okay. Okay then, everyone. Take care. Love.